All right, class, welcome back. So today we're going to continue a more general discussion about mass equilibrium. Mass equilibrium is trying to understand the consequences of the second law with regard to spontaneous changes or how matter flows from one state to another. We've thought about this a lot in the last week or so in the context of phase transitions, namely how matter flows from one phase to another, say how a collection of water molecules initially in a vapor phase might spontaneously transition to a liquid phase. Those sorts of physical contexts we've been able to say some generic things about in the context of phase diagrams and critical fluctuations. We're going to turn our focus now on questions of more chemical relevance and specifically think about how matter flows from one place, say one solution, to another, or how matter flows from one molecular arrangement, say a reactant, to another molecular arrangement, say some product state. And it turns out in a specific case, we'll be able to say quite a lot about such spontaneous changes, both microscopically and their macroscopic consequences. And those cases, however, are pretty ubiquitous throughout actual chemistry. Those are cases where the solutions that we're dealing with are dilute. So an example of what we might be thinking about in context of mass equilibrium in dilute solutions could be characterized with the picture I've shown here. Imagine you have some flask, and in that flask are two different liquids, say water in the blue, oil floating on top in the yellow. I might imagine that in that solution there are some solutes. I'll draw these little black dots. Those solutes can, if say they start in the aqueous phase, repartition themselves into the oil phase as well. How those solutes decide they're going to partition themselves between those two phases, and as a consequence of the second law, will be determined by the relative chemical potentials of those solutes in those two different phases. Now, when the solutions are dilutes, if we were going to blow this solution up, so we now have some more microscopic perspective on the solution. We still won't render those solutes with any intrinsic molecular structure. But if we thought about their statistics, if those solutes are dilute, we can imagine that their statistics are the statistics of uncorrelated molecules. So the state of one of those solutes, say that one, or that one, is statistically independent. And we know a lot about the implications, the formal implications of uncorrelated fluctuations. For example, we know immediately that the partition function for that set of solutes is going to factorize. It's going to be something raised to however many solutes I have. Let's imagine I have n solutes. Now, what the details of that partition function is going to depend on what those solutes are. In general, we can imagine that we can break that partition function up into two different pieces. Some translational part, times some what I'll call Q non-translational part. So in this component here, we're going to imagine storing all of the intramolecular fluctuations, things that have to do with, say, the orientation or vibrational state the molecule might be in. as well as any interactions with the solvent. So this non-translational part could be quite complicated if we needed to actually consider in how a solute might interact with a solvent. Those are probably complicated, but if those solutes are sufficiently dilute, its interaction with the solvent is going to be independent of whatever any other solute is doing. Now that translational part, we've thought actually a lot about. The translational part of a partition function for a molecule being somewhere in space is just going to count up how many regions of space that there are that that molecule could visit. So specifically, I could imagine gridding up space in some region, say delta x cubed in volume. The number of places I could put a particle is just the total volume of the system in that resolution of delta x cubed. So the number of translational states for n particles is just the volume in some resolution raised to the n. So the translational part of the partition function, we can always write down, and it's always pretty simple. We then are left with q non-translational raised to the n. And if those solutes are indistinguishable, we know we have to account for the potential for permutations. So the partition function will have that factor of 1 over n factorial to account for that correctly. So we have just, in some sense, solved for the partition function of a pretty complicated situation, a situation of a bunch of n solutes in a solution. And we factorized it into a part which is simple to count, places we can arrange solutes in a volume V, and a piece that might be hard, all those intramolecular fluctuations and interactions with the solvent. But immediately there's a consequence of this specific form of the partition function. And we can note that by reminding ourselves that the chemical potential for those solutes well, a way to define that chemical potential, say mu, is how the Helmholtz free energy changes with the number of those solutes if I were to fix T and V, the other natural variables of the Helmholtz free energy. And what is super convenient is if we're considering a system where energy can be exchanged with the surroundings, so the Helmholtz free energy is a natural function of the temperature, which dictates how much of that energy is exchanged. We know a relationship between the Helmholtz free energy and microscopic fluctuations as encoded by this partition function. If we remember, the Helmholtz free energy is equal exactly to kBt log that partition function. So actually the chemical potential is minus kBt, which I can pull out of that partial differential because T is being held constant. The derivative of log of the partition function with respect to n. So the fact that we have solved for the partition function lets us immediately derive the chemical potential for those solutes. So let's do that. So the chemical potential is equal to minus kBt ddn. And now let's write out the log of the chemical potential, or the log of the partition function. So we have log of 1 over n factorial. Ooh, that looks ugly. We'll deal with that in a second. We'll have log of v over x cubed. That whole thing is raised to the n. If I take the log of something raised to the n, I can pull the n out in front. And then the same thing is true with n times log of q non-translational. All right. So the second and third terms on the right-hand side of that equation have simple forms. This, however, The log of n factorial is a little scary. You all have probably already dealt with that a little bit on your homework. Let's discuss it in a little bit of detail. So n factorial, we remember that n factorial is equal to n times n minus 1 times n minus 2, blah, 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 blah. We're going to need to take a derivative of that function. So we need to have a representation of that factorial function, which we can take a derivative of simply. Now we're going to use the fact that in most macroscopic systems, n is very large, and for large n, log of n factorial is well approximated by n log n minus n. There's a good representation or an approximation to log of n factorial, which is given by the so-called Stirling's approximation. Now, those are functions whose derivatives we know how to take. So now we can actually compute that chemical potential by noting then that d log of n factorial dn, well, it's just taking the derivative of the right-hand side of Stirling's approximation. That'll be, to a good approximation, log n is the first one of those terms. Let's write that out again. So n log n by chain rule gives me a log n plus a n over the derivative of log n, which gives me 1. The derivative of minus n is minus 1, so those cancel, so I'm left with just log n. So putting this together, the chemical potential is equal to minus kBt. I get a log n from that first derivative with a minus, because I flipped the argument of the log. And then I have a plus log. I can combine these two terms, a log v with some resolution, and a q non-translational. Now I can actually simplify that even more by multiplying through this kBt. I'll have a kBt. Now log, I have minus log n times the minus, so that's log n minus log v. I could put n over v together and I'll get the density. I can measure that density in some units, delta x cubed. Then I have the q non-translational left over, where the density is n over v, like usual. Now I can actually do one more thing. I can multiply top and bottom of the argument of this log by some reference density rho naught. Okay. And then if I do that, I can write the chemical potential down as kBt log rho over rho naught plus kBt and all the complicated bits. I'll have a rho naught. I'll have those units of my resolution all over q non-translational. Cool. So this has now a very simple form for the chemical potential of this solution. We have two pieces. We have a piece that is simply dependent on the solute density. and accounts essentially for the different translational states all the different ways we can arrange spatially those solutes. And we have another piece which is complicated, and so we have to unpack a little bit. We've isolated all of the density dependence and the translational dependence in the first term. In the second term, well, one nice thing about it is that it's independent, therefore, of density. So that's nice. But it's going to depend on some arbitrary choices. You'll see that the resolution we decided to count states in still appears, and it also depends on what this reference density we're going to choose is. So that's kind of a bummer. It describes interesting fluctuations. All the non-translational parts of the partition function is isolated there. So that's nice. But by the same token, that means it's going to be very difficult to compute. What turns out to be useful is that this part of the chemical potential exists just in tables. You can go look them up. It's some function that's going to depend on the temperature, the reference density, and what solute and solvent it is. But because of that, it's also going to vary with things like the temperature and the pressure, because that's going to modulate things like how the solute interacts with that solvent. So for simplicity, let's go ahead and just give it a name. Let's call it the standard state chemical potential. We'll give it a little superscript O and explain and demonstrate explicitly that it depends on temperature and pressure through the dependence of the interactions of the solute with the solvent. So if we put this together, then chemical potential is this standard state piece plus a simple function of the density. Let's highlight that because it turns out to be an incredibly useful equation. But let's remind ourselves explicitly how we got here. We got here by working with solutes that were uncorrelated. So this is only valid for dilute solutions, which is another way of saying small densities, small concentrations. And let's state explicitly that this rho naught essentially defines a standard state. The choice of how we partitioned these two terms in the chemical potential set what we must call this standard state chemical potential. And part of that choice was that reference density we chose. That's useful because by construction, when the density is equal to rho naught, the chemical potential, reference part plus kBT log rho over rho naught. Well, when rho is equal to rho naught, log of 1 is 0. The chemical potential is just that standard state chemical potential. And now there are lots of common choices for a standard state. So one that's often used is to say that the reference concentration is equal to 1 molar. Another common choice, which is not so much used for solutions, but for gases, would be to say that rho naught is 1 atmosphere per kBT. Why ever would you use that as a standard state? Well, mu is equal to mu naught plus kBT log. If rho naught is an atmosphere per kBT, well, density over kBT is what the cool kids call the ideal gas law. So we would just say that this is equal to the standard state chemical potential plus log of the pressure of that gas over a reference pressure of 1 atmosphere. Hence why it might be useful for gases. Another common choice is to say that rho naught is the density of the solvent, which is just the number of solvent molecules over the total volume. In such a case, rho over rho naught is equal to the number of solutes over the number of solvents, each over V, but the factors of V will cancel. And if we have a dilute solution, then the number of solvent molecules is much, much larger than the number of solute molecules. So this is approximately N solute over the total N, which we recognize as just the mole fraction of solute, thus getting rid of the units entirely. So we have the chemical potential is this reference piece, kBT log the mole fraction of solute. Now these are just manipulations for this equation. It's important to remember that the standard state is going to depend on our choice of convention. What we decide to use is rho naught, but the overall chemical potential does not, because we're just distributing terms between the two pieces on the right-hand side of the equation. Okay, so this is the ideal form of the chemical potential. It really plays the same sort of role as the ideal gas law for telling you about the pressure. So to make some sense of this, let's first try to understand this standard state chemical potential a little bit more. All right, so let's think concretely about a situation in which we have, say, 2 different phases, maybe 2 different solutions. We'll call 1 and 2, where we have solutes that are partitioning between those 2 phases. So the chemical potential, we remember, is how the Helmholtz free energy changes with number of particles at fixed temperature and volume. Well, dA dV, I could write that as delta A, delta N, and the limit that N is small. The smallest N I can change as 1 molecule. So mu has an interpretation as the Helmholtz free energy change when I move 1 molecule, say, between these 2 phases. So the Helmholtz free energy from moving 1 molecule from phase 1 to phase 2, if we use our expressions for these dilute solutions, well, we'll have the standard state chemical potential of phase 2 plus kBT log rho 2 in some reference minus the standard state chemical potential of phase 1 plus minus kBT log the density of the solutes in phase 1 rho naught. If we use the same, say, standard state conventions for both phases. So that is then equal to the change in the standard state chemical potential plus kBT log rho 2 over rho 1. So let's reflect on that. We've just sorted out that if we were to move one molecule from phase 1 to phase 2, that we can actually compute the change in the Helmholtz free energy for doing that, and it will have a piece that gives us a change in the standard state chemical potentials plus kBT log the difference in the ratio of the densities of those two phases. So that second term, kBT log rho 2 over rho 1, that accounts for translations. That's what we noted at the beginning. It essentially says, how many ways in space can I put a solute? So if we moved a particle from 1 to 2, but keeping the position fixed, that change in Helmholtz free energy would be equal to just that change in the standard state chemical potentials. So what's the Helmholtz free energy? We define the Helmholtz free energy. Its usefulness is encoding how much work is done in a system or how much reversible work can be done by a system. So if we move a solute from phase 1 to phase 2, not allowing it to explore different translational states, we find that the work required to do that reversibly is just the difference in standard state chemical potentials. By contrast, at equilibrium, when those solutes have partitioned themselves in such a way to minimize the Helmholtz free energy, it must be the case that mu2 is equal to mu1, or that delta A is 0, it's minimized. So that implies that kBT log rho 2 over rho 1 is equal to minus delta mu of the reference. If I rearrange that by dividing both sides by kBT and exponentiating, I get rho 2 over rho 1 is equal to minus beta, that difference in standard state chemical potentials. Or if I remember what those standard states were before I introduced those reference densities, it was, if I go even further back, just the non-translational parts of the partition function. So at equilibrium, if I want to know how much of the solutes are in phase 2 relative to what their concentrations are in phase 1, all I need to know is what the non-translational parts of the partition functions are in phase 2 relative to phase 1. If I can count up the number of states that a solute can fluctuate around in those two different phases, I can predict what the intrinsic preference of those solutes are for the different phases. So let's give it a concrete example for a solute going between the liquid and the vapor. Imagining that our solutes are volatile. So again, pick out a little piece of our system. We have some liquid down here. We have some vapor up above, and we have solutes that could be either in the liquid or the vapor. If they're volatile, they'll have some vapor pressure above the solution. From this expression, the density of solutes in the vapor relative to the density of solutes in the liquid is going to be equal to e to the minus beta delta mu of that reference, that change in the standard state chemical potentials. Now, that quantity is a function of temperature and pressure. Both could change the number of non-translational states that those solutes could explore. In the vapor, the density of solutes is equal to beta times the pressure of those solutes. In the liquid, the density of solutes is equal to the mole fraction of solutes times the density of solvents. So putting those together, we have the density, the pressure of solutes in the vapor is equal to the mole fraction of solutes in the liquid times a function of temperature and pressure. That's just a number independent of the density or amount of solutes there are. Let's call that K sub H, right? It explicitly depends on temperature and pressure. This is an equation you might have seen before. Think all the way back to Chem 1A. If I wanted to ask you, for example, how much a specific volatile solute, like say a gas, like carbon dioxide, how much is soluble in a liquid, so what the mole fraction of carbon dioxide is in liquid water given some vapor pressure that you're exposing to that liquid, you would have computed that with a coefficient, this KH, known as Henry's law, known as the Henry's law coefficient. So indeed, what we've just derived is the Henry's law relationship that tells us for a given vapor pressure how much solute we will be able to solubilize in a solution. But this is just a consequence of mass equilibrium equation and the dilute solution equation for the chemical potential. So all of that was thinking about how molecules might partition themselves in space, so between different phases. Let's imagine molecules partitioning themselves between different molecular species. This is a question of really chemical equilibrium. Now, the simplest chemical equilibrium I can imagine is just taking two hydrogens in the gas. Those hydrogens might come together and form H2. I might imagine something more complicated, like, say, an acid in solution dissociating. Or maybe even more exotically, questions of chemical equilibrium might be, say, how a ligand binds to some protein, forming some protein-ligand complex. Those are all cases where I have mass equilibrium, matter deciding what state it's going to preferentially be in. Atoms flowing between two different bonding arrangements, or molecules associating or disassociating. In all of those cases, I can imagine a thought experiment whereby I run any of those reactions forward just a little bit. At, say, fixed temperature and pressure. If I'm working with fixed temperature and pressure and I'm letting N fluctuate, the natural thermodynamic variable to think about is the Gibbs free energy, which is a natural function of temperature, pressure, number of particles. At fixed temperature and pressure, the Gibbs free energy change is just given by a sum of the chemical potentials of each species times how their numbers change. If I run this reaction forward a little bit and say dN molecules of H2 dissociate, then I have, let's say, form, running it forwards. Then I have minus in H2 is equal to minus dN. And for every molecule of H2 I dissociate, I form two H atoms, so dNH is going to be then twice dN. So dG is going to be equal to mu H twice dN minus mu H2 dN. At equilibrium, that has to be equal to 0, which means that the chemical potential of H2 must be equal to twice the chemical potential of H. So the condition of equilibrium when I'm repartitioning mass, say between two chemical species, is going to depend on stoichiometric numbers like how many species are produced when I run the reaction forward, how many consumed are produced when I run backwards. Similarly, for those other contexts like acid-base dissociation, the chemical potential of the associated acid at equilibrium must be equal to the sum of the chemical potential of the excess proton plus the conjugate base. The chemical potential of the protein-ligand complex at equilibrium must be equal to the sum of the chemical potentials of the protein and the ligand in isolation. For all of those cases, if all species are dilute, then we know that the chemical potentials of each species take on this specific form of a sum of some reference standard state chemical potential plus kBT log the density of that species over some reference density, which means with the constraint of equilibrium, we can actually work out what the concentrations of those reactants and products are relative to each other. For example, for H2 dissociation, we just worked out that the chemical potential of H2 at equilibrium must be twice the chemical potential of monatomic H. So if H2 is dilute, its chemical potential is the sum of its standard state chemical potential plus kBT log its density over some reference density. That must be equal to twice the standard state chemical potential of atomic hydrogen plus twice kBT log the density of atomic hydrogen over its reference. If we define delta mu of the reaction as being mu of H2 less twice the standard state chemical potential of atomic hydrogen, and we note that if I have twice log x, that's equal to log of x squared. I can rearrange this equation up here. I have mu of the reaction by bringing this over to the left. I have kBT log rho of H2 over rho naught. When I bring this term over to the left, I will get a minus log rho H squared over rho naught squared. All of that will be equal to 0. Rearranging further and exponentiating, I'll have rho of H2 in the denominator, rho of H squared in the numerator will be equal to e to the minus beta delta mu of the chemical reaction times one factor of that reference density. So the concentrations of the atomic hydrogen squared is over the concentration of H2. So the concentrations of the reactants multiplied together over the concentration of the product has a specific value at equilibrium in terms of that delta mu of the reaction and the standard state density. Again, that's some generic function of, say, temperature. So you would call that function of temperature an equilibrium constant. We've just derived the law of mass action, or what microscopically equilibrium constants actually mean. So if you can compute partition functions, you can predict the course of chemical reactions. It's as simple as that. These sorts of equations are known as the laws of mass action. And we should remember that this is simple only because we're considering dilute solutions. The definition of an equilibrium constant, often abused, really is only valid when we think about reactants and their products being under dilute solution conditions. Otherwise, we wouldn't be able to so cleanly separate out the density dependence over on the left-hand side of that equation from, say, the temperature dependence over on the right-hand side of that equation. So this is general. We could have done this for our acid-base reaction as well. The concentration of protons, their conjugate bases, over the intact acid would be equal to that reference density, either minus beta, whatever standard state chemical reaction we would have found there. And in general, in a solution, that equilibrium constant would be dependent on temperature and pressure. In a gas, if those species are dilute, the ideal gas law constrains that the temperature and pressure are related to each other. So I can choose which one I reference. Okay, so that's pretty interesting, I think, right? So we worked out from a microscopic picture dealing with uncorrelated fluctuations of solute molecules, some consequences that you are all very well familiar with. You know from long ago, from your first chemistry classes, how to compute equilibrium constants in terms of ratios of concentrations. Now you actually know what those mean microscopically. If you can compute partition functions, just counting, you could predict equilibrium constants. So we'll explore this a little bit more in the next few lectures as we kind of continue our way through a discussion of mass equilibrium.